Okay, without further ado, Dr. David Kolesky from the Jennifer Lewis Lab.
Hi, everyone. So yeah, thanks for having me, and I'm happy to talk about our work that we're doing up at Harvard. So I'm going to quickly tell you guys a little bit about what our lab does generally in Jennifer Lewis's lab, and then a little bit about my work on 3D bioprinting of vascularized tissue structures. So let's just get to it. So our group primarily works with this filamentary printing approach, where we create these extremely viscous and highly concentrated suspensions, and allows us to print in complicated 3D shapes. So the video that you just saw going on the right is actually a 30-micron nozzle of conductive silver ink printing from a bottom silicon wafer up about 1 millimeter to another wafer. And you can see that it's actually spanning completely in 3 dimensions. So let me show you again, but you see that it's actually completely self-supporting. And the way we achieve this kind of response is actually through a precise control of the ink rheology. And so what I mean by that is we want the ink to rapidly flow through the nozzle. So to do that, we impart a shear thinning behavior. And after the ink is extruded through the nozzle, we want it to set rapidly. And so to do that, we impart a yield stress behavior. So you have to apply a certain amount of stress to the ink. It extrudes out of the nozzle, and then it sets exactly where you put it when you stop applying pressure. So it allows you to build these complicated shapes. And our group has applied this sort of conceptual framework to a lot of different materials approaches, a lot of different material systems. So you can see this plot is sort of an arbitrary materials parameter. So it's the Young's modulus. So you can think of it as the stiffness of the material as a function of the feature size that we can achieve. And you can see that we're spanning orders of magnitude here, from sub-micron down to up to the millimeter range. And so commercial 3D printers operate primarily in this regime, but using this approach, we can actually access this entire face space with very different materials, ranging from ceramics, metals, and also polymeric inks. And so there's a lot of applications that we've tried to hit using this approach, but primarily the way we think about it is we're not just trying to use 3D printing to tackle different complicated shapes, but we're actually trying, and forms, but we're trying to impart complicated functions and achieve using materials that current 3D printers can't achieve to create these complicated objects. So a few examples are these 3D printed antennas. So what this is again, this is a silver ink that's being printed conformally along this glass hemisphere. We also have people in our lab that are printing lithium-ion microbatteries. So there's a small lithium-ion microbattery inside of this packaging, and that battery is about a millimeter on each side. We also have people that are working on stretchable sensors and lightweight composite materials. So again, I wanted to show these examples in a little bit more detail. But yeah, you can see the silver ink is actually printing on the inside of these conformal antennas as well as the outside. You can do it both ways. And these have extremely high performance. And when you map them to theoretical simulations, they actually behave exactly as you would want for pure silver, or very close to pure silver traces. So with the printing microbatteries, you can array these in a lot of different shapes and spaces. You can do them in series and parallel to improve performance and hit whatever you want. But essentially, a guy in our lab developed an anode ink, a cathode ink, and he printed them in these high aspect ratio interdigitated patterns. And they don't actually touch, so you can then flow an electrolyte in between them, and you can charge and discharge these materials, creating a small battery. And then we can also make these wearable sensors for biomedical applications, where we can print these conductive sensors inside of highly elastomeric matrices. And then just by straining them, you change the resistance of the trace, and you can wire those up, and you can get feedback for the amount of strain that you're applying to these sensors. But my main focus as a researcher is actually trying to recreate and develop a renewable source and manufacturing method for human tissue. The real application here is really twofold. On the pharmaceutical side, there's billions of dollars that are spent on drugs that have ultimately failed to reach market. And if we had a a faster fail method, sort of a preclinical phase 0 trial, if you will, that more appropriately mimicked the response of drugs in the body, we may be able to bring those numbers down and actually have more drugs being developed over shorter periods of time. The other side is the clinical side, and tissue engineers have been working for the last 15 years on trying to recreate various pieces of tissue. But the state of the art is really only being able to create two-dimensional, simple replacements, such as the skin graft that I'm showing on the right. So the real problem and challenge with addressing both of these applications is that human tissue is extremely difficult to mimic. It's extremely heterogeneous. There's multiple cell types arranged in very intricate architectures. The human body has hundreds of cell types. The architectures are extremely heterogeneous, and there's huge gradients that span moduli, orders of magnitude in moduli over very short distances. But the other thing is that human tissue is highly vascularized. And in fact, every cell within the body of dense tissue is about 100 to 200 microns away from the nearest blood vessel. And if it's any further away than that, the cells will actually become hypoxic and can die. So my approach, and the group's sort of idea here, is can we take the ability to pattern different materials together and recreate tissue? And so the 3 phases that I try to focus on are recreating extracellular matrix materials, vascular networks, as well as patterning cells, and putting them into 3-dimensional architectures in ways that could more appropriately mimic that of tissue architecture. And so to do that, we developed a few different inks. We developed hydrogel-based inks that mimic the extracellular matrix. We developed fugitive inks that allowed you to pattern channels within cell-laden hydrogels. And we developed cell-laden inks that allow you to actually print cells directly adjacent to these other inks. So here's a video of one of the processes. So the first ink you see is actually just a structural border ink. It's a PDMS-based material. The second ink you're going to see is actually the fugitive ink. And so this ink has the uncanny ability to be printed at room temperature, but by cooling it down below a certain temperature, it actually liquefies. These next 2 inks you're going to see are actually cell-laden hydrogel-based inks. And then we're going to come in and on the next layer, repeat the structure with a slight modification so that you can get this layer by layer building of this tissue structure. So keep in mind, everywhere that we're printing that very clear, smooth ink is where we're going to get an open channel in the final structure. And so the next video here is after we've cooled down the structure below its critical melting point, we actually liquefy the fugitive ink, come in with a light vacuum, and now you can actually suck away the fugitive ink, and you're left with this open, pervasive vascular network throughout the tissue structure. And then if you zoom in and look at this under fluorescence, you can see where exactly we patterned the 3 different inks. So the green and the blue are 2 different cell types that we printed directly, and then this is an open channel that we then lined with endothelial cells, which are the same types of cells that line your blood vessel in the body. And so after we create these, we then hook them up to these perfusion devices that we've developed. And so we actually 3D print these interface gaskets and then machine these holders for them. And then we hook them up to external pumps, and we can flow nutrients and drugs and growth factors through them. And moving forward, we're working on developing new extracellular matrix inks for all the different tissues. You can imagine any tissue you're trying to tackle has vastly different composition of their extracellular matrix, and you need to be able to address that materials challenge with new inks. The other thing we're working on is creating more composite vascular networks. So a blood vessel is not simply just an endothelial lining, but it's also got structural smooth muscle cells and connective fibroblasts around the outside. And we're working on trying to mimic all 3 of those. The other thing is trying to guide and direct the growth of new capillaries off of our larger vessels. So in the body, like I said, every cell is within a few hundred microns. And we don't envision constructing every blood vessel. We kind of want to stick to the larger vessels and have the smaller ones grow on their own. And then ultimately, we want to move to more mimetic vasculature that appropriately mimics each specific organ or tissue system we're looking for. The other thing that's really important is actually increasing throughput of printing. So 3D printing has been traditionally a very slow method. So using a single nozzle to build up layer by layer can take a very long time. And so what we're developing are these high throughput print heads that allow you to take a single stream of ink, bifurcate it over and over out to 64 or 128 unique or individual outlets. And then you can pattern large areas in one pass. And so here's a picture of a part that we printed using this method, and this part actually took about 24 hours to print using a single nozzle, but once we switched to this multi-nozzle array, it only took about 22 minutes. And you know, it's actually very large. It's about 20 inches by 20 inches. And you can also take these microfluidic printheads and marry them to each other and offset them by half a period, so you can print multi-material structures, which again is very important if you're trying to achieve heterogeneity in structures that aren't just monolithic materials. And you can do a lot of interesting things like space them out different amounts, and then you can print not just parallel lines, but you could also print different objects in parallel. So that's what we did here on the bottom right. But moving forward, you know, really what we're thinking about is if you're trying to recreate a piece of tissue, you don't want to have to do the entire thing. And it's actually very naive to think that we could even do that. And so if we could use our expertise in sort of top-down manufacturing, but also harnessing sort of the bottom-up assembly processes of biology, there's probably a median point in the middle where you don't have to create everything, but you create enough that sort of sets the development down a certain pathway. And so that's what we're working on now and trying to do. And ultimately, you know, one of the grand challenges you could have, you could envision is for maybe tissue or organ printing, where you could acquire a patient-specific model, generate a complex tool path, recreate the structure using a bioprinter or another manufacturing approach, and then perfuse it and get it ready and then implant it eventually. So, and on that note, I'd like to thank you know, my advisor, Jennifer Lewis, and then also the rest of the bioprinting team, who are my close collaborators, and the rest of the Lewis lab, and some people and funding sources at Harvard. So with that, I'd like to take questions.
Hey, hey, David, can you hear me?
Yeah.
Great. This is John Rowley.
Hey, John, how are you doing?
Great. First, thanks for talking today. This is really great. I'm glad the technology works. So, thanks for joining us from Boston.
Yeah, of course, of course.
Yeah. So the questions there was a couple questions earlier on resolution and printing and the importance of it in tissue and organ printing. So yeah, what do you think is I mean, I don't think we need quite the resolution as we get into, you know, 3D printing a sensor, but I mean, what do you think are the key resolutions maybe in the tens of microns that are going to be required in order to make this stuff work? Is it hundreds of microns? Is it tens of microns? Or
I think it's a great question, and you know, I think largely the honest answer is we don't know yet. And I think there's a lot of value in being able to pattern sort of the structural protein around the cell and guiding cells that way. But that may be overkill. You know, cells produce their own extracellular matrix. You can actually direct them in a number of ways to do that. And so that may not be needed. And again, the vascular network that we're printing is sort of on the scale of 100 microns and larger, and creating the smaller capillaries, we're really hoping that we can encourage that through angiogenic processes. So, you know, on the creating vascular side, we hope that it's not needed to go smaller because, you know, a lot of you guys are probably familiar, as you go to smaller and smaller features, the resolution actually cubes your build time. So the build time goes as a factor of, you know, to the third power, the smaller and smaller you go. So, you know, if you want to construct a liver with single cell resolution, it would take months and months to print, and you would have to keep the cells alive that entire time. So I hope that it's not the single cell level, but it's hard to exactly say.
Great. Yeah, thanks.
Yeah.
Next question.
So your slide you presented using the bottom up and the top down approaches and finding that equal balance in the middle. So what kind of work is doing in trying to get differentiation of printed cells? What are your comments about that?
I'm sorry, can you repeat the final part of the question? You were talking about the top down and bottom up slide. I missed the final part. Yeah.
Printing the essentials, probably undifferentiated cells, partially differentiated cells, and then letting that differentiation process occur.
Right.
in situ with that. Do you have any comments about that?
Yeah. So I mean, ultimately, you know, one of the biggest challenges in tissue engineering, any type of tissue, is going to be cell source. And so if you're able to guide the cells in situ inside of your tissue structures, I think it gives you a big advantage to having to rely on pre-differentiated cell types. So I think sort of the way to think about it is potentially having a subset of structure that you've already fabricated, but then have sort of blank slate cells that you could then guide through some means externally.
Another question here.
Yes, this is Julie Longton. I'm wondering with your bifurcated head design on your output stage there, what sort of problems are you running into when it comes to the difference in pressure between the multiple output nozzles? Do you see some sort of a shear, or are you getting differences in layer heights or anything of the sort?
Well, okay, so let me clarify the question. Was the question, what kind of problems do we have in the multi-nozzle print heads?
Yes, because when you're using that multi-nozzle, I noticed that your material doesn't arrive all to the end at the same time, which is going to cause could cause different pressures.
Yeah, it's a great question, and that's actually was something that we struggled with for a while. Was manufacturing these devices with high enough precision that we actually got even flow across the entire our final generation. And we actually did a little bit of modeling and figured out that if we're within 5% of tolerance across the entire array, we actually get very, very good uniformity across the entire thing and equal diameters of our filaments. But yeah, the big drawback is if you have a clog upstream down one of the generations, that could deviate flow around the clog and lead to non-uniformity across the entire face.
Thank you.
Yep.
So I ask one more quick one. Sorry, what do you think is the lowest hanging fruit for the first application that this could actually be used in the tissue side? I'm sure you thought.
Yeah, it's a great question. So I think the lowest hanging fruit broadly is going to be some sort of in vitro diagnostic or disease model, not necessarily jumping straight to the therapeutic side. So if your question is in the therapeutic side, I think the lowest hanging fruit could be some sort of vascularized tissue flap or a small piece of tissue patch that you might be able to recreate. But on the in vitro diagnostics or disease modeling, I think there's a few different ones. I'm not sure if I'm at liberty to say exactly what we're working on now, but yeah.
Thanks a lot.
Yeah.
So with that, maybe there's more. We have our final speaker in queue. I hate cutting off rock star like Dr. Kolesky, but I hope you understand. There's somebody else in queue, and we've been waiting a while. Going on.
Yep.
Thank you so much. Really appreciate it. Yeah.